Okay, folks, we've talked about scalar multiplication, which is a number times a vector. Now we're going to talk about vector addition, and vector addition is actually a vector times a vector. The definition is pretty straightforward, so let's take a look. Definition. Suppose that we have V, let's call that one AB, and W, that's another vector, we'll call that one CD, are vectors. Then the addition, V plus W, is going to look like this. If we take that AB and we add on CD, we add them simply component-wise. That is, we add the x coordinates and we add the y coordinates together. So this thing is equal to A plus C, comma B plus D. When you add one vector to another, you get a vector, and you just add the first components and add the second components together. All right? So that's the idea behind vector addition. We're going to look at some examples, and the first example I will do in a little bit more depth, part A, and draw a picture, and then later examples I will do more quickly and primarily algebraically. So they say perform the vector addition and simplify as much as possible. This is example 22.11. And part A is 3 comma minus 5 plus 6 comma 4. That's what we're after here. So this is A, 3 minus 5 plus 6, 4. Let's go ahead and give ourselves coordinate axes here. Okay. First, I want to give the answer. The answer is straightforward, and then I want to talk about what that answer means. So the answer is just, well, we add the first components, 3 plus 6 together, and we add the second components, minus 5 plus 4 together, and then just simplifying, we get 9, comma, negative 1. That's our answer, 9, comma, negative 1. And that's simplified as much as we can. That was supposed to be an easy problem. Let's go ahead and draw these guys. So I'm going to draw the first one, that 3 minus 5 in orange. And 3, let's see, 1, 2, 3, and minus 5, 1, 2, 3, 4, 5. That one is down here. Okay, this is the vector 3, comma, minus 5. And then let's go ahead and take a look at the vector 6, comma 4. For that one, let me see, we go over 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. That's going to go right about there. Okay. So this is our vector W, and this was our original vector V. And then the question is, let's look at, we'll put it in red, the result of adding them, which is 9, comma, negative 1. So this is 6, 7, 8, 9, comma, negative 1. It's right about there. And I think from this picture, it's not totally obvious where the heck that came from. But there is actually a lovely picture we can draw that entirely captures this. And it is as follows. If you imagine adding vectors as like following the path of one vector from the origin, and then following the path of the other vector, but thinking of that path as starting down here where the last one stopped. So it's like we want to move that second vector down so that it starts here. Let's go ahead and do it. Ooh, this is going to give me a whole bunch of things I don't want. Let's undo that. Here we go. I just have to be clever about my selecting. I think I can just go like that. One more time. Let's try. Here we go. Okay. So what I'm going to do is I have a copy of my vector w, and I'm just going to move it so that the base is right at the end of my vector v. And you'll notice what happens is if you follow first the vector v and then the vector w, you end up at exactly the end point of the sum vector. And it works not only that direction, but it works the other way too. Let's see if I can do this. Here, whoops. If you were to follow first the vector w and then move the vector v out so that it starts where w ends, so follow first w and then v, you also end up at the same place. So v plus w is the same as w plus v. It is this vector in red is the vector that gives you the result v plus w. The shape that this makes around the outside, these lines are parallel here and parallel here. That's a parallelogram. And you can make a parallelogram whenever you add vectors to show you where in the picture the result of adding those vectors is going to be. Okay. As far as the answer, the solution to this problem, it is simply what we wrote before. It's 9, negative 1. That's it for this. Go ahead, try adding the remaining B, C, D, and E, and then we'll go ahead and do them together. Okay. Part B. Here we go. This one is 5 times the vector negative 6, 2, minus 7 times the vector 1, negative 3. Now this is not just vector addition, but we first have some scalar multiplication with these vectors, and the way that we handle it is we do the scalar multiplications first, and then we add the resulting vectors. So let me see. To begin, we do 5 times negative 6 and 5 times 2. And that gives us, let me see, negative 30, 10. And then here you can either multiply by 7 and keep a negative in the middle, let's make it a subtraction, or you can multiply by negative 7 and change that to a plus in the middle. I'm going to take the latter option. I'm going to change that to a plus, and here I'm going to multiply by negative 7 times 1 and times negative 3. So negative 7 times 1 is simply negative 7. Negative 7 times 3 is positive 21. Now we have to add these vectors together, and we add them component-wise, which means first we add the x's. Negative 30 minus 7 is negative 37, and 10 plus 21 is 31. That's the result of our addition. All right. Well, that's our answer to part B. Let's take a look at C. C says 4i plus 9j, which is means that we're going to have to remember what are these vectors I and j. So there's like a little recall here. There's two very special vectors. They're unit vectors, and they're the ones that point in the x direction. That's I, it's the vector 1, 0. And j is the one that points in the y direction. And that's 0, 1. Okay. So what is this is just replacing. This is 4 times the vector 1, 0 plus 9 times the vector 0, 1. This is scalar multiplication here. I multiply 4 by the things inside. And scalar multiplication here, I multiply 9 by the things inside. However, since these vectors are so nice, you're going to see this is quite easy. 4 times 1, 0 is just 4, 0. Because when we multiply that 4 times 0, it remains a 0. And similar, 9 times 0, 1 is just going to be 0, 9. Now we have two vectors added, and here we add the x's and we add the y's, and this is going to be 4, 9. Now, there's supposed to be a takeaway from this example, which is that when you look at an expression like this, 4i plus 9j, that's just a shorthand way of writing the vector 4, 9. It's writing it in terms of the component, the sort of x and y vectors, the I and the j. And when you see an expression like this, number times I plus number times j, once you multiply it out and then add the results, you're always going to end up with a vector with this number in the x and this number in the y. Okay. That's something that will help us later. That's part C, and our answer is the vector 4, 9. Let's take a look at D. Now, for this one, we're going to need a reference to it, so I'll just go ahead and grab a copy and pop that in here. So for part D, find 2v plus 3w, where v is equal to negative 6i minus 4j, and w is equal to 10i minus 7j. There are various ways of attacking this, and they sort of depend on how you want to approach it. I'm going to do it like this first. I'm going to first just figure out what v and w are equal to as sort of standard form vectors. V is negative 6i minus 4j. And we say whenever you have a vector of the form something times I plus something times j, you always end up with just that vector, minus 6 minus 4, consisting of those two numbers. And we'll have, that was v. For w, we'll have a similar thing. This is 10i minus 7j. And that's equal to, of course, we could, once again, replace I with the vector 1, 0, and j with the vector 0, 1, do scalar multiplication, and then add vectors. But this is a common situation. It shows up enough that you should just get familiar with it. This is going to be the vector 10, negative 7. And now we would like to find the expression 2v plus 3w. And I'm going to use the expressions for v and w that I found just before. So this is equal to 2 times minus 6 minus 4 plus 3 times 10 minus 7, which is equal to, well, doing scalar multiplication, multiply the 2 through that first vector is going to give us negative 12, negative 8. Multiplying 2 times minus 6 and 2 times minus 4. And then plus multiplying 3 through, that's going to give us 30 and negative 70. Now, final step, adding these two vectors together. First we add the x components, minus 12 and 30 is 18. And minus 8 minus 70 is minus 78. And that is our final answer for part D. This is the vector 2v plus 3w, where v is the vector minus 6i plus minus 4j, and w is the vector 10i minus 7j. All right, that's D. We have one more of these guys. Let's do it. I'll go ahead and grab a copy. And then we'll pop that in here. This is similar, but the vectors are not given to us in terms of i's and j's. We have a vector v, which is 8, radical 3, and a vector w, which is 0, 4, radical 3. And we just want to find minus 3v plus 5w. Well, let's go ahead and do it. This is going to be similar to the last one, but I'm not doing the very first step where I translated the v and the w into standard vector form, because they're already in our standard vector form here. So minus 3v plus 5w, that's what we want to find. And I'm just going to substitute for v minus 3, that v is 8, radical 3. And then plus 5 times w, the w is 0, 4, radical 3. That is equal to, well, we multiply through and we get minus 3 times 8 is negative 24, and minus 3 times radical 3 is just minus 3 radical 3. And then multiplying 5 in here, 5 times 0 is just 0. That one is handy. And then 5 times 4 radical 3. The 5 is not in a radical. We're going to multiply it by the number in front. The 4, 5 times 4 is 20 radical 3. Like so. Now what we're left with is addition of vectors. And so we are going to take this vector and this vector and add them together component-wise. So add the x's and add the y's. Negative 24 plus 0 is negative 24. And the next one, I'll just be careful and copy it down properly so that I don't mess anything up. Minus 3 radical 3 plus 20 radical 3. That's what we need to work on. And what's nice about this is that both of these have a radical 3. They're like radicals, which means we can add the numbers in the front. And that will be our final simplification step. This is negative 24 stays in the x, and negative 3 plus 20 is positive 17 radical 3. There we go. Our final answer here is the vector negative 24, comma, 17 radical 3. That's it for this example. There's one more example, and then we'll be done for today.